Hello, I'm Dan Sandine, and this is about a 50-year of stereo display systems. And so that's like, more than less than 1 minute per year. And thank you very much for inviting me to do this talk. How many people have seen this video that I'm about to play?
In 1965, the pioneer of computer graphics, Ivan Sutherland, realized computers held the key to a much richer kind of visualization. He wondered what it would be like to reach through the screen itself and surround himself in a simulated world. This experimental helmet gave the user the illusion of being inside a three-dimensional world. As he moved his head, so the pictures changed accordingly. The technology was barely able to handle a simple geometrical world in those days.
Now I can ask the question again. How many people have seen this video? Oh, good. So, of course, many people coming into the kind of VR world think that VR is entirely a head-mounted display phenomenon. They also think it's kind of new. And this video, which many of you have seen, is from 1965, and it was attached, it was so-called a sword of Damocles because there was a rod coming down from the sky that got dragged around by the head-mounted display. And this had all the properties of a modern VR system. So in 1969, I was invited to University of Illinois at Chicago's art department to bring computers into the art curriculum. Now, this is quite extraordinary because art departments, strangely enough, are not very forward-looking. They're kind of dominated by art historian types, and they're kind of more backwards-looking. But this particular art department was a third-generation Bauhaus, and their concept was to do a synthesis of industrial design in the cybernetic age, as it was called at the time. One of the first projects I did there was this analog image processor modeled after the Moog Model 2. And it is a computer. It does addition and subtraction and division and multiplication. And in terms of floating point operations, it actually has the power of a supercomputer at that time, although the flops were much, much floppier, about 6 bits, I think, or 7 bits. In 1973, Tom DeFonte came. And he brought with him the GRASS software system, which took advantage of these, took advantage of this holographic display and was designed to be a language that was easy to learn and the kind of language we could kind of like basic in a sense. It was an interpreter, but it was actually designed to do graphics, so it's something that an art student, for instance, could learn.
Is
28,000 words of RAM. Six megabytes. So I wanted to show that. It doesn't really have much to do with stereo displays, but how much fun it was back then. In 1976, we developed the first data glove, and there's a picture of it there. And our concept there was that we were very influenced by musical traditions, and so having a hand like that with all these fingers and thumb could allow us to control a lot of analog variables at the same time, which then would affect images on the screen. So it was very much real time and very much influenced by performance ideas. Part of the trouble at that time is actually storing this information, getting it onto film or videotape was actually hard. So doing things live became a more important part of the tradition than it is now. In 1976, we, with Larry Cuba, just a very good editor, a very good filmmaker, he had one of his films is called Calculated Movements, and that's kind of like his whole way of doing business. He does these highly abstract, wonderful animation. So you look him up on the internet and look at a couple of them. We did this briefing room scene here. In other words, what they were chasing through the whole first movie was something produced at EVL. And there's a picture, a little bit clearer picture of the holographic display. There's no pixels involved here. It draws lines on the screen. That's the reason for the name holographic. It was before the invention of the frame buffer. In fact, when the frame buffer got invented, computer graphics just stopped moving. Well, it had this tradition of being kind of live and moving before. But in this period, what's really probably most important about it is that it kind of organized a principle of operation, you know, where the artists organize projects, help visualize data, create media. The artists are supported, like they get paid, and get their toys to do their own work, inspired by science often. And scientists get the deeper insights into their data. One of the things you may not realize that in this time period, scientists did computational science by using remote computers, typically, you know, controlled by card decks, and they walked out of those buildings with big boxes full of fan-fold printout, full of numbers. Really an impossible situation to deal with by modern terms, and so we plugged into that need, and that's what ended up kind of supporting us through this whole thing. And basically, EVL, you know, delivers art intelligence to scientists, systematically teaches the arts and technology, and less systematically teaches the art to the scientists. And it creates new and hardware software systems and supports their user community. And that's been the most important thing about the success of EVL. Support typically includes enough information to copy the tech themselves, or when possible, enabling companies to build and sell the system for those people that have more money than time. My first real 3D, I was a hobbyist stereo photographer before this period, but my first 3D display design, we're working with Ellen Sandor doing these scholograms, and there's one in the back corner, which I forgot to turn on. So we get a chance to look at that on your way out and experience. So it's a barrier strip system. You're probably all very familiar with this. But the eye looks through a set of slits and it sees various columns, the way to think about it, behind the image. So you can encode several images which are fed out by being at different angles. In a sense, what we did was to do a computer simulation, in a sense, of the kind of classic 3D camera here. Behind this 4 lenses would be a lenticular screen, which is kind of has more light efficient than a line screen. The line screen is really the pinhole equivalent of these lenticular screens. And behind that was some film. We basically simulated that whole process by having a CRT with a slide, just kind of basically a view camera kind of approach, and printed the different columns down. It was a kind of simulation of a Bonnet camera. It gave rise to a large body of work, a lot of it computer generated. And the computer generation basically was an off-axis perspective projection, which could be implemented with a modern frustum command, but at that time you had to do a shear and then a standard perspective project. Now I'm going to talk about virtual reality. I mean, one of the real irritations is that people seem to think that virtual reality is isomorphic with head model displays. and aren't aware of the fact that, and this, not speaking to this community, but speaking my frustration with the, every time you look up VR, it has only to do with head mounts. But to me, the definition is a system that supplies a large angle of view, in this case with by having a magnifying lens next to a small screen. The way caves do it is you get close to a very big screen. You have stereo vision as a part of this experience, and you use various forms of, you typically have to wear glasses, although there are systems that do it without glasses, for instance, the scologram. And then the real important thing is the kind of first redefinition of perspective, where you actually get the perspective from where your eyes are, and not where some computational obelisk is in making the conversion from 3D to 2D, because it's kind of 2D on the screen. And then in this case, we have tracked glasses that get the orientation of the head. And we were a little extra confused about it at the time, but the best way to think about caves is they're a mixed reality system when on the people side of the display surfaces, and then they're a full virtual reality system on the other side. And that's kind of, that actually took us a little while to figure that out, because people claim, well, it's not virtual reality, you know, because you can see yourself. The first classic cave was shown in 1991. It was a Master of Fine Arts show. And in 1992 at SIGGRAPH, and over 10,000 people saw this, because it really is kind of a theater. You can move people through this environment in the first 2 years. And here's a video from so that was fun. I haven't seen that for a while. So another term, which many of you maybe understand, is to measure the sharpness, one uses visual acuity. It's kind of based on a eye chart. It turns out that 20/20 vision is the ability to discern 1/60th of a degree of angle, and hence be able to read these letters. And it roughly translates into 60 pixels per degree is what you need to match human average human vision. So 2020, of course, is considered normal for all you people that aren't wearing glasses and don't go through this every year. 2015 is actually fairly common in youth, and 2030 or corrected is better, is required to drive in most states, and 2200 is in general considered legally blind. So the first cave was had a acuity of 2092, which is not all that good, but we did, of course, improve it over time. But head-mounted displays, the sharpest of them, had about 2200, which is legally blind. So we could make this joke: they're going to teach, brain surgery in a display that is for legally blind people. Another very important part of caves is, if you imagine rotating the head like this, back and forth, in a head-mounted display, the whole world has to rotate around by 30 or 40 degrees. So it's actually very disorienting. You can see in this kind of case, really what's happening is the perspective on the screen is changing by a couple of inches in viewpoint. And it's really a very stable experience. And that was probably one of the biggest advantages of the cave, because it was so much easier on computational resources, because you didn't have to have extraordinarily high frame rates to produce an experience that wasn't nauseogenic. And so what are they good for? And I think what they're particularly good for is, of course, the visualization of complex data. That would probably also apply to head mounts in all these different areas. The theater aspect of this VR is that it very directly supports small group interaction. And that's, of course, a very important thing in all the areas where people can discuss things as they're seeing them. And be able to see their body language. You have trouble seeing the eyes because of the glasses, but you know where they're looking anyway. And it's a very natural environment to carry on discussion. Now, here's a short hit of the cave development, all the way up to 2017, which was the last new cave that we had something to do with. I should make a moment that I'm really talking about the work here that's originated at Electronic Visualization Laboratory, and then around the turn of the century, Tom and Larry Smar, I'll discuss later, moved out to the West Coast where the weather's better, and developed at that time called CalIT2, which is now called Qualcomm Institute. So I'm really covering the work at both of those institutions, which have kind of interchangeable parts with EVL. By the way, Qualcomm Institute is not in any sense owned by Qualcomm. That's through the philanthropic arm of Qualcomm. We do have various relationships with the Qualcomm, but they're in no sense of research. We are in no sense a research division of Qualcomm. One of the more successful displays, because it's a kind of cutback from all these fixed projectors and stuff, was the Immersidesk. And it's a single screen stereo at that time, still time division multiplex for vision. We got a kind of a drafting table format with the idea people spent a lot of time designing parts which could be handled well in that kind of environment. It's in an AV case, you can ship it around, and the angle of the screen is can be changed easily by turning a crank, and so you could even show PowerPoints in stereo to your group too, right after you've been using it to design with. We found that we thought people would design on these. That really didn't happen that much, but design review happened on them a lot, where they could go over the 3D models and the 2D information and all of that. So it was a very successful display, one of our most successful displays. Now, how many of these kinds of things got copied is a little hard to determine, so these are very low ends predictions. There are predictions, for instance, of caves to be up to 1,000. I don't know where they got them, but people predicted that. So all of this is pretty well tracked. The GeoWall is a great example of how we operate. There was over 500 built. They're based on two projectors, so it's passive stereo. And along with it, we developed all of this software that geologists like to use both to do research and to describe their work. And it was adapted by a community of people, and that's been our model. I think without without developing communities, we'd be a very different kind of organization, and we wouldn't have been nearly so successful in keeping the operation running for this many years, and hopefully many years into the future. Projectors have a number of real problems, so we wanted to move to panels, but the panels at the time, LCD panels, are very slow. In fact, they're still kind of slow, so you couldn't do the field sequential stereo, and there weren't ones built in with polarizers on the front like you can get now. I still think you can get those now. It used to be easy. It used to be consumer TVs after this period, but recently. So the research that we did was we used barrier strip technology, just like the scalograms that I described earlier. And I think the unique thing was the way we'd prepare for that was to virtually think of the projection points which follow wherever the eyes are around, and they would then project the correct image onto the barrier strip so that you would see in stereo. There's a part of Cave 2 in the way, but this curved thing is the kind of biggest implementation of it. Here's a little video about it. Okay. Oh, does that include 15 minutes more? So the features of this barrier system, oh, by the way, we also had single screen versions that did have camera tracking of the eyes. First of all, it could do high quality stereo from panels, and at that time there was no other panel-based solution available. Lenticular screens or these alternate line polarizing screens were not available. And that didn't start to come in until about 2006. For several years, this was the only way to do it by panels. The problems with Barrier are, in my view, the worst problem with Barrier is that it's really a single-person viewing system. The the character of the projection means the person standing next to this projection ends up, with bars moving through their vision. It's not quite nauseogenic, but it's not a comfortable position. And so there are really only 2 or 3 of these built, and maybe a total of 5 or 6 if you consider the single panel ones. The next thing I did was take the same concept and map it into lenticular displays. These are, of course, displays that put out a fan of images, in this case 8 images. This 3 by 6 aleoscopy HD displays was 19 feet by 5 feet. It was really quite a wonderfully bright and dynamic display. And it used the same kind of computational technique. One of the problems with that kind of display, you can imagine there would always be a bar in one of the panels, because they aren't precision aligned, but you can align them in software. And so when it's head tracked, it actually keeps right on your eyes. But also, you can just do it for the sweet spot of a room. Like if there's a 12-foot behind this panel where people are, you put it in the center of that space. And the display really worked quite well for that application. Now, the next projection cave was the Star Cave. And it was made up of 3 HD screens per wall, total of 5 walls. Part of the reason we did this pentagonal arrangement was it's easier to get into a more circular realm and have a little bit of space in the center. And also non-parallel walls helped with sound, because being with these were now hard shell. They weren't like they weren't like shower curtains. They were pieces of glass, and it's a very difficult sonic environment to operate in. And the non-parallel nature of the walls helped a little bit. Here's a picture of someone in the Star Cave. This was a 3D panorama. One of my also areas I'm not going to talk about was developing cameras for producing these systems. You can see the little white nose. That's because there's a projector onto the floor that happens to be illuminating the nose. And you can see a little bit of color variation between those things, but it really is a very comfortable and immersive system. The next one I'm going to talk about is Cave 2, which is a current system. What's interesting about it is it kind of combines the advantages of a conference room with full VR. You can hold classes in this, you can have a reasonable number of people in it, and here's a video about that system. Hopefully. Oops. Well, that's going to make it easier. Well, okay. I'm going to go on to the, say what?
Is this a video? Yeah.
Okay, great. Thank you. How pretty to do. A lot of people want to get their pilot's license to land on Mars. So the next cave after that was developed at Qualcomm Institute. It's called the Sun Cave, and it's made up of a bunch of these Sony consumer TVs. The big advantage of these prosumer and consumer is that it's fantastically less expensive than the commercial markets. This just to handle that issue of you have to really address these things fairly straight on to get them to work. The basic solution is to kind of curve them like that so that you're always looking at them. You get a bunch of different geometries that do that. And this one is a kind of shell-shaped thing with parts of the displays overlapping other parts of the displays, but it actually, with the proper perspective projections and stuff, it's the barriers there do not cause any problems. And this is I happened to shoot this astronomical panorama, and so every once in a while people say, well, for panoramas out at infinity, what do you need stereo for? And the answer is that, well, like in this case, you can see there's water. I shot this picture when I was, more than knee-deep in water, wearing waders with my tripod. And when you're in there, you feel like you're literally, like waist-deep. Even if we turn up the stereo, it's waist-deep in water. We turn down the stereo, it's knee-deep. But knee-deep's about the right one. So I have a practice that has to do with doing a lot of outdoor work and developing cameras for this work and related work. So here's some other pictures of that. These are, again, from stereo panoramas. And then here you can, for instance, you skateboard in Luxor if you want. Take a moment here. This is over on the left. There is Greg Daw. He did all the industrial design for all caves up to Cave 2. Cave 2 was done by Jonas Talantis. But all the rest of this stuff, he was the industrial designer and mechanic for doing all of this stuff, and it's really important. There's Larry Smar. He was the director of the first supercomputer center in Urbana. And then Tom DeFani, my partner in crime for the last 55 years. Really what this represents is that all of this wouldn't be possible without rich connections to science and being useful to scientists, so they would spend the extraordinary amounts of money that it takes to actually make this stuff happen. And just to reflect what was in the original cave, with any luck, this will play. Nope, okay. So this happens to be remote, so it won't be solved by the other problem, by the other one. So, but that's good because I'm running out of time and I want to show a stereo movie at the end. This is a stereo display conference, right? So I want to make a couple more comments about how you handle groups of people in these kind of environments. This is a top view of the Sun Cave. And so one is for stereo. For you're a single person in the cave, everything's great. As you would address the screen, the stereo is perfectly good. But behind you, if somebody's looking at the screen, the eyes are reversed. So that for groups of people, we developed this on the stereo system. And the simple model is we have several, but one simple model is you just calculate each panel based on a line from the center of the cave perpendicular to the panel. And so that produces some discontinuity at the edges, but with all these panels being so close together, it's hard to notice it. If you really look for it, you can see it, but you don't feel it at all. And for tracking, we typically pass the head cap around. We like that form because then they're in control and they get their view of it. So if you can keep people addressing the same direction in small groups, that works all right. And if it doesn't, then you basically turn off tracking, put it in the center of the cave. And that works pretty well for people too. But you keep the wand active so you can still control things. So the Sun Cave resource, this is also typical of Cave 2, has a huge amount of compute resources. We have 17 CPU nodes with 2 ARCs 3090s each, driving the total of 70 screens. There's a 40 gigabit connection to a switch, 100 gigabit out to their Scenic, which is the network on the West Coast, and lots of local storage and stuff. And part of the economic model of these caves is we rent those GPUs out to people trying to do artificial intelligence processes. And it isn't like they pay us money, but we get upgrades and they pay for repairing them, because keeping these things running is a serious problem. And so that direct connection and it really works very smoothly. You're going to do a demo and you push a button and everybody gets carefully shut down, and then you do the demo and then you turn the demo off and then everything's open again for people to use it. And these things probably are idle 80% of the time or something, and so that all becomes very useful. And it's actually how we get paid. So here's some other configurations based on those kind of panels. This is a very nice configuration for small groups, and it's quite portable. So we take that on the road every once in a while. Here's a version that's you get a virtual image under the screen. There's haptic feedback too, so you can manipulate directly with force feedback the object that you're seeing properly with moving your head around in 3D and stuff. So what I would like to do now is try to see if we can show a video, a stereo video. Now this video I did in 2006 and 7, and I lost the stereo copy in some series of disk crashes and stuff like that. And so I haven't seen a stereo version of this since its original version in 06. Lance Long, a very hardworking person at EVL who does a lot of things, including AIT, I got him to mount a bunch of old discs, and then I was able to find a copy of this, which I processed on the plane on the way here. So I haven't seen this for a while. And if it's 5 minutes long, and so it should work out pretty well. you. It was really nice. I haven't seen it for a long time. It's really nice. I get this illusion of kind of brushing me in the face sometimes. Did anybody find the stereo particularly disturbing in this piece? Oh, that's good. All right. So I just want to take a moment to thank a whole bunch of people, the hundreds of graduate students literally hundreds of graduate students we've had in the lab, especially the Director Emeriti, Tom DeFonte, Jason Lee, Maxine Brown, and Andrew Johnson, who've kept EVL operating over all of this time, and the current director, Michael Pekka. And also to thank the staff at there, and Larry Smar and Ramesh Rule from Qualcomm Institute. Thank you very much. Questions?